Okay, so this video is Gauss's law continued for the spherical symmetry. Um, so just to remind you, we've been working on this already, and we've done some examples. We did the spherical symmetry with the charge all on the surface, which would have been what happens with a conducting sphere. And now we have to address a uniform charge density, which I'll do next, and then I'll address what happens if the charge density is some sort of function. But remember, in the spherical symmetry, one thing that we do need is that the charge density has to be perfectly radially symmetric. So it can be a function of r at best, but it can't be a function of theta or phi. So if you haven't seen spherical coordinates before, it essentially means that you can have that the charge density changes with radius, but you can't have it there be like a left-right asymmetry or an up-down asymmetry. That makes things more complicated. And if the charge density itself doesn't vary except with radius, then the electric field cannot vary except with radius. I call this the curtain test in the last video. It's this kind of symmetry test, and if you can't tell from the charge that something's been changed, you shouldn't be able to tell from the electric field either. So we can safely conclude that the electric field of this thing, this is going to now be the uniform charge density. This is going to definitely be radially symmetric. So it is going to be radial. So the electric field is going to be something like that, just from symmetry arguments. And I do want to remind you that we've already learned for those same symmetry arguments that when you get outside of that charge density, the moment you get outside, the electric field immediately, not eventually when you get far away, but immediately, quote unquote, collapses right into that of a point charge. So that'll make our lives a lot easier. And so I'm going to do the same thing with this. I'm going to find the electric field everywhere, inside and outside. I'm going to find the voltage everywhere, inside and outside, and that's the goal here. And we are going to do it in terms of rho here, since we're given the information in terms of rho. And I guess I should also mention that I'll call the size of this sphere capital R, as I did previously when the sphere was hollow. So let's go ahead and do this. Well, first of all, if I drop in a Gaussian surface here, so this again, remember, for the spherical symmetry, my Gaussian surface is also a spherical shell. It's chosen specifically so that the normals are exactly aligned with the field. And rather than having to do some complicated flux calculation, I've picked my surface so that it's just EA cosine of 0. So these angles between the normal vectors and the for the Gaussian surface and the field is just 0, and that gives me EA cosine of 0. This is plus, I guess. The most complicated it could be is a minus. Of course, if this is a minus charge, then the field lines will be radially inward, and they'll make a 180-degree angle to this outward-facing normal. So I guess I should mention that's the most complicated it could be. But since I am using a positive charge distribution, I will get positive flux. And let me again remind you that this becoming this, if that doesn't happen, if you can't choose a Gaussian surface that makes the flux calculation very easy, then you probably shouldn't be using Gauss's law in the first place. That's not what Gauss's law really does. So essentially, the secret, the big kind of dirty secret of Gauss's law is you can impress somebody by showing them this top statement. But this right here is really where you most of the time will start. Okay, that's where the calculation ends up being almost immediately, and that's of course a much more easily manageable law. So let's go ahead and get started. My catcher, well, this is a spherical Gaussian surface, so the area of this is 4 pi r squared. And that is, of course, the radius of my catcher, so I try to reserve little r for the Gaussian surface. And then the charge enclosed, well, all of it, that's all of it's enclosed. And then if I'm going to do this in terms of charge, or instead of charge density, instead of charge itself, the total charge, of course, will be Q times, Q is rho times this, the volume, okay? And of course, I want the entire volume because all of this is enclosed. So here you have to be a little careful. Do you use big R or little r? Well, of course, we don't have charge enclosed all the way, the entire Gaussian surface. It runs out and it's not only enclosed up to capital R. So only up to capital R is where you actually have charge sitting. And let me remind you, what's the volume of a sphere? It'll be 4/3 pi r cubed. So make sure you understand why this is not little r here, okay? So I'll go ahead and put that in, rho 4/3 pi big R cubed, and then don't forget the epsilon naught. We get a substantial amount of cancellation, 4 pi's go away, and then I can go ahead and write the electric field will be rho big R cubed over 3 epsilon naught, and then 1 over r squared. So there we have it. That's the electric field, and this is outside, where we have that we are outside the sphere. It is proportional to 1 over r squared, but it sure does not look a whole lot like this. Remember, we said that the electric field immediately outside should collapse to that of a point charge. I'll leave it to you to convince you that it absolutely is agreeing with this. This is just kq over r squared. The reason it looks different is because, of course, instead of q, we have this expressed in terms of rho. So you can, of course, have the risk relationship over here. Q equals rho times this is how you relate the two. And of course, this one has a k and this one has an epsilon naught. But I will let you confirm algebraically that this is just q total over r squared. And in fact, an alternative way of doing this is just to basically use this kind of collapse theorem here and just say, okay, well, the answer is definitely going to be kq over r squared, and I'm just going to figure out what q total is here. So I don't want to dissuade you from doing it that way either, but in a lot of these problems, we do want to work in terms of rho instead. Let me go ahead and start working on the inside. What's the electric field inside? So for that, let's do inside, which is to say my Gaussian surface is inside, so that it's going to be less than the big R. Always worth drawing again, just for clarity. So my object has a radius big R, but now my Gaussian surface, I'm dropping it in here, and remember, my Gaussian surface is just a means to test what's going on with the electric field. And so I'm putting it inside there because I want to know what the electric field is inside there. So how is this different? Well, it's not really much different. In fact, there's only one thing that changes. Same thing. I purposely put my Gaussian surface like this because I know that the field, whatever it is, it's got to be radial. And so how does it differ from before? Well, still EA, my catcher is still that Gaussian surface. It's still spherical. Area is 4 pi r squared. And then the only thing that changes now is that my enclosed charge, well, now, of course, my object itself is still the same charge, but I haven't enclosed all of it. So I've only enclosed a portion of that charge, okay? So here, the difference is that now, remember I purposely said before, don't use little r, because when your Gaussian surface is way out here, you don't enclose, the charge doesn't live all the way up to that. But now the charge does live all the way up to here. And in fact, that is going to be some subset of the total charge. So the only thing now is that my Q enclosed is going to be rho times V enclosed. And V enclosed is going to be 4/3 pi little r cubed. And now it's the opposite. Make sure you understand why it's not big R, okay? So it's the opposite. Here we used, when we're outside, we use big R, and when we're inside, we use little r. That is, in fact, the only change in these calculations. Let me put the last one here side by side so you can see. It's going to be rho 4/3 little pi little r cubed, okay? So let me use a color I haven't used yet, orange, okay? That right there, when you're inside, it's little r. When you're outside, it's big R. That is, in fact, the only difference between this line and this line, okay? Now, that might not seem like much, but that, in fact, will give a very different character of the electric field inside. So let me work out what that is. So still have some cancellation, 4 pi goes away. And now this is actually the same r. Before, it wasn't. So this is the little r, this was big R, couldn't do anything with that. Now, this is little r squared, little r cubed, so we get a lot of cancellation here. And what our end result ends up being here is rho r over 3 epsilon naught. And in fact, that is the electric field, which is actually linearly proportional to r, okay? So that is my result inside. So r is less than big R. Now you might say, well, hold on a second. That does not look like kq over r squared. And that's probably fine. That's because we're not outside it, right? We shouldn't expect it to collapse onto kq over r squared because we're inside. This actually, if you wanted to, you could still, this is still kq over r squared. The only difference being is that the q involved is only q enclosed. And since q enclosed goes as the third power of r, right? As I expand my radius, the q will be enclosed as the third power of where I am, and that gets divided by this. As I go out, my catching area only gets bigger. That ultimately comes from here. That only comes goes off as r squared. You can see how this ends up being proportional to r itself, okay? So again, if you wanted to work it out from here, you could. You just remember that when you're in spherical symmetry, you're just basically using point charge stuff. It's just that now I have to be careful because the q, I can't use the whole q. I only have to use q enclosed, okay? So that right there actually goes ahead and gives me my electric field for both the inside and the outside. It might be good to kind of make a little survey here. So if I'm inside, r is less than big R, I have, and let me write it like this, rho over 3 epsilon naught, and I'll put the r here on the outside just to remind myself it is proportional to r. And I put over here E vector, so I probably should, that would have an r hat on it. So let me just say this is the radial component, or the magnitude if you like. Since I'm using positive charge. Okay, so, and then outside, big R is the smaller one, so I'm testing my Gaussian surface outside, then copying my previous result over here from the last page, looks like this, and that's proportional to 1 over r squared. So let me go ahead and draw what this looks like. I'll just draw the magnitude here. That would be generic to both a positive and negative charge. I'm not doing a negative charge here, but so let's go ahead and mark off here. Of course, one of the most important cut points here is the big R when I'm inside versus outside. Outside just goes off like a point charge, proportional to 1 over r squared. And then inside, it is linearly proportional to r, which means that if r is 0, I get nothing. And then it does grow linearly, and as I'm about to show you, it does exactly connect with this, okay? So it exactly connects. If you plug in r equals big R, so that you put your Gaussian surface right at the surface, you actually will, I'll let you confirm that both of these formulas will give the same result, which is the maximum electric field which is going to be rho big R over 3 epsilon naught, and that is the maximum value of the electric field. So that's kind of nice because we don't have any kind of weird discontinuities or anything like that, at least in terms of the value. Obviously the slope is a bit funky, but we don't actually care about the slope of this graph. That produces nothing. That is of physical interest. But the value here is perfectly well controlled. There's no weird jumps or anything like there was in the previous example. And so let me take a look at why this makes sense, okay? Why is it that the electric field grows linearly with R until you get to the surface and then dies off as 1 over R squared? So imagine for a moment that I were a hypothetical positive charge that's mobile, and I would be free, you know, I had a little tunnel to go through or something like that. So I could kind of freely move here and subject to the electric field of this, the particles or the charges around me without, you know, any issue. Well, in the middle, that positive charge would just stay stuck. It's no wonder, because the other positive charges in the sphere that are all around are going to repel it all equally. It's exactly the same reasoning why the electric field is 0 in the middle of the ring. If you look back to homework number 2, why is the electric field 0 in the middle of the ring? Well, you just have all the charges around it are pushing on it equally, so it ends up being nothing. Now, what about on the journey of this charge outward? Let's say okay, if it's just going to sit in the middle and not do anything, let's pick it up and move it just slightly over here. Well, now the charge isn't quite symmetrically all around it. It's almost symmetrically all around it, but there's a little bit more charge on the left than on the right. So if I move this positive charge here and I kind of draw it here, kind of separate this out, there's a little bit more plus charge on the left versus the right. So now the push on it, well, it's almost still 0. There's going to be a slight push to the right, and the reason why is that there's more plus on the left hand side here repelling it than minus charge on here repelling it. So it's no wonder you get a tiny little bit of force there, and of course that's due to the tiny little bit amount of electric field. And you can see, of course, so on and so forth, as this charge gets closer to the surface, well, now all of this other positive charges to the left, all of it repelling it violently, and there's nothing on the other side pushing it back anymore. So it's no wonder that you get the maximum electric field and maximum force right when you get to the surface. That's because you're as close as you can be to this charge while having it still all coordinatedly kind of pushing you away. And then after that, as you go out here, of course, the charge is, the sphere is still on all to one side, but you're starting to put distance between you and the sphere. So at that point, it's no wonder that the force on this particle will start to die, and so will the electric field. So that's why conceptually it makes sense that the electric field will grow until you get to the surface, and then it will shrink again, okay? So that's a little bit conceptually on why this all makes sense, okay? So now, let's go ahead and attack the voltage. So the voltage, well, of this thing. Oh, and the other thing I guess I should mention, I meant to mention this at the beginning, so I'll just throw it in here. How exactly do you get something like this? How do you get a sphere of uniform charge density? This can't be a conductor, because the conductor, the charge would all repel to the surface, okay? And for an insulator, we learned in homework 2 that the insulator, the charge essentially resides where you put it. So how in the world did somebody create this? Did someone go with a pair of tweezers and pluck electrons off evenly through this entire thing, including throughout the volume of this thing, and somehow reach in these magic tweezers inside this thing and pluck these off and make this a uniform charge density? You're right to ask how in the world you could make this uniform rho sphere. And to that I say no comment, okay? All right, so voltage. let's talk about voltage. Well, first of all, I'm going to go ahead and note that since the electric field outside is a point charge, the voltage will be 2. So the electric field is kq over r outside, and so the voltage, of course, will be kq over r outside as well. Now, I will go ahead and copy my previous result here for the electric field. That will be rho big R cubed over 3 epsilon naught 1 over R, and R squared, excuse me. And of course, if the only difference between these two formulas is this square versus being there versus not being there, we can safely conclude that the voltage is the same deal if it's expressed in terms of rho instead of Q, and it's expressed in terms of epsilon naught instead of K. I can safely conclude, well, all this other part must be the same. This one has a squared and this one doesn't. So I'm done, good to go. If I wanted to sketch what the voltage looks like, okay, I can already start doing that. So outside, it's going to look like just like a point charge. It's going to go off as 1 over R, and I'm pretty much good to go there. So really the only thing I need to do here is what's going on inside. And let me remind you, how do we do this? Well, if we have the electric field function, then we integrate. The negative of the integration is the change in voltage. So I'm working inside, so I better use the electric field inside. And I'm going to start integrating at the surface. And of course, that is where the old electric field formula is no longer good, and the new one picks up. By the way, I should have mentioned that if you're wondering, when you're right at the surface, the two actually agree, so there's no problem here. Both of those formulas actually agree on the surface, so there's no ambiguity about when we're switching to the new electric field formula. So what we're doing is we're using the electric field formula inside. We're starting our integration at the surface, and we're going in, and let's leave it open at some final value so we can get a function here. But remember, this is going to have to be some value inside. If we put in the electric field of the inside, we have to commit to not integrating somewhere where that electric field is not actually valid. So let me go ahead and put it in. Integral from big R to little r. And I'll put in my formula, rho r over 3 epsilon naught dr. And when I do that integration, that will give me the voltage final, which will be the voltage at some random value inside. And its difference from when I started, which is the voltage at the surface. All right, so let's go ahead and do it. If rho is constant, you just pull it out. 3 epsilon naught as well. And we get this integration r dr. And of course, that's good old r squared over 2. And I have to evaluate that. Before I even do that, I guess I can take the 3 and the 2 here, make it a 6, minus rho 6 epsilon naught, and then r squared minus big R squared. And remember, that is going to be the difference between the voltage where I end up inside minus the voltage at the surface. And in fact, let me go ahead and throw that on the other side. So this is my voltage function. I shouldn't box it yet. I need to finish that off. But so first of all, as a check, this right here, if I'm at the surface, which is to say little r is equal to big R, I get that, no surprise, the voltage here is the same as the voltage of the surface. So the voltage at this point is the voltage of the surface. So what should we use for that? That's a free constant, of course, that we always have. This is again where we go back to that story of being mindful of voltage origins. This already has a voltage origin set, okay? If it's a point charge formula outside that at r equals infinity, the voltage is 0, That is our reference. We cannot choose that to be 0 again. That would be having two origins in the same problem. In fact, what we want to do is we want to make sure, and this is discussed in the last video, we want to make sure that our voltage function is continuous. Okay, in other words, no jump cuts. We can force that to be the case, and I talked in the last video about why we want to make sure to do that. And so in order to do that, well, all we have to do here is find out what does the outside function tell us the voltage should be here. Okay, this is the voltage at the surface, and we want to use that value. So let's go ahead and put it in. We have the voltage function on the outside. So the outside function, it tells us that the voltage at the surface should be rho big R cubed, just using this function right here, 3 epsilon naught, and I evaluate that at big R, and we get some cancellation here. That's rho big R squared over 3 epsilon naught. That is the value that we want to use. So that makes sure that the new function, the voltage function on the inside, actually concurs with what the voltage should be on the surface with the voltage function on the outside, okay? So let's go ahead and throw that in. And now we're starting to approach the final form of the voltage function on the inside. Now let me copy over from the previous page what I had before, and then I'll throw in that value, okay? Minus rho over 6 epsilon naught, like that. And then the voltage function that is passed to this from the outside function is rho big R squared over 3 epsilon naught. Okay, so now this is my final function. There's nothing really else I need to do to it, but I do notice that it is possible to simplify this. This term here, with of course this multiplied in, and this term actually do combine very nicely. And what you end up getting is minus rho little r squared over 6 epsilon naught, and then you get plus rho big R squared over 2 epsilon naught, and that's my final function here. And again, this is not meant to be like a something that you just grab and use wholesale. I want you to be able to go through this whole process yourself. I do want to mention that this thing here, where I do a little bit of simplification, does not work for the cylinder, which I'm going to do next. So you're lucky if this constant here, this voltage value you're passing in from the other function, is going to play nicely and simplify with the other stuff you get from the integration. That does not necessarily always be the case, and if not, your function may just, no big deal, your function may just look a little bit messier, and this voltage value that's on the surface that's being passed in may have to sit on the side and kind of be just off by itself instead of getting to play with the other stuff that you get from the integration. Okay, so what is this thing right here? What does it look like? It's proportional to negative r squared. The rest of these are constants. Remember that big R is the size of the sphere, so the only active ingredient in here is the radius, and there's a negative, so it's an upside down parabola. And let me show you what it looks like. If I add it here to this graph, it goes like this. Okay, so that's proportional to negative r squared. Okay, how do I know that it looks like that? It's an upside down parabola. How did I know that it connected up like this? Well, I made it connect up. Remember, I made it so that instead of looking something like this, I lifted it and made sure that I connected that function to the previous function. I don't want jump cuts in my voltage function, and I can make sure that that does not happen. Okay, so there is my voltage function. I guess it's worth kind of resketching here. My voltage function looks like this. There's my big R. It looks like this, kind of parabola that then goes like this. And I do want to, let me resketch the electric field function as well and show you what that looks like. That's E. R, and that looks like this. Okay, so let me put in the proportionalities here too, so you remember them. This is proportional to R. This is proportional to 1 over R squared. Over here, this is proportional to negative R squared, and this is proportional to 1 over R. Okay, so we already sort of talked about why this made sense. Let's talk about why this makes sense. So we talked about why is the electric field 0? Well, and if you're right in the middle, everything's pushing on you all from all sides, all around, so you get nothing. Then as you start to have a little asymmetry, that'll allow you to push the charge away, and then it reaches a maximum force and maximum field on the surface, and then it dies down. This, in that context, makes sense as well. Remember that, so right here, let me remind you that since I integrated the voltage, or integrated the field to get voltage, it's always worth going back and remembering that the opposite is true as well. The electric field is a negative dV dr, which means it's the negative of the slope of this voltage graph, slope of V versus R. So we go back here. What's the value here of the slope? 0. So that's why the electric field is 0. Okay, the slope here is 0. Okay, so if you and then the maximum slope is right here. The maximum slope is, in fact, negative rho big R over 3 epsilon naught. Well, how do I know that? Well, remember the minus of the slope is this value, which I already found previously, right here. Okay, so I'm sort of double checking. This is the maximum negative slope. That's the maximum positive value here. The slope of this graph is the value here. And notice here that as an added bonus, these not only does the voltage graph stay continuous, it actually does stay differentiable. Okay, this slope is actually exactly the same from this function and from this function, and it has to stay that way because this is not only continuous but also differentiable, because the slope of this has to give the electric field, and the electric field is very well defined here. So so this is actually, even though we stitched this voltage together from two different functions, it actually, these two functions stitched together not only to join up, which of course we forced it to be, them to join up, but it also, when they stitch together, they stitch together with the same slope. So it's not like you have this weird kink where the slope is undefined. They actually do agree in terms of their slope as well. And then of course from here, the negative slope gets less, which means that the positive electric field here gets less. You can even look at these, right? What's the negative derivative of R squared? It's going to be proportional to R. What's the negative derivative of 1 over R? It's going to be 1 over R squared. So again, just using your calculus ideas, you can do a lot to confirm that these graphs make sense. Okay, so remember that the essential relationship between these two, the negative sign aside, which is always has to be, you have to remember that, but the general flavor is you integrate going this way and you take the derivative going that way. Okay, if you want to think of it conceptually, let's again talk through it. I like to think of this again as kind of like a skateboard ramp. If you had a little skateboarder up here, they might have lots of voltage and lots of potential energy, but at this point it's flat, so if they could just sit there, no energy exchange available, no field, so no force. But then if they pushed off, they'd go slowly at first, and then shoom, and then shoom, like that. So again, at this first bit, you have the ability to lose voltage ever more rapidly. The potential energy and kinetic energy would increase. Potential energy would decrease, kinetic energy would increase, and then here you're still going to keep speeding up, but you're going to asymptote out on a certain final speed. And so as your ability to lower your voltage stops being a thing. So again, As you go outward, as R increases, then you will find that on a positive charge or skateboard or whatever you have that the voltage will decrease, the potential energy will decrease, and the kinetic energy will increase. Once your voltage approaches zero, then you will have the maximum. You have wrung the maximum amount of speed out of this particular system. So that right there, that is the uniform charge density and uniform charge density sphere. And then what I need to do now is simply just tell you the final case. What would you do if rho was a function, okay? And remember, it can only be a function of r. So what does that look like? Well, if I have a sphere, okay, let's say it might have not very much charge toward the middle, and then I have a lot more charge on the edge or something like that. And let me try to do my best to sort of simulate what that would look like. I'll do a second round here of charge just to indicate that it's really highly charged density on the outside. And in the middle, not much. But it is still radially symmetric, okay? We can't just have that there's more charge on the left versus the right. You have, by radially symmetric, again, we mean that if you go out in any direction, you'll have the same experience. So if you go out to the right, you'll see less charge density at first, more charge density later, and then same thing if you went off in any direction, you'd see that. And so what you then have is that if we draw ourselves a little bit of a spherical shell, and this is now a thick shell, okay? Remember, this is charge density, so it does need a volume to exist in. So we might say that there's lower rho on this shell, which is closer in, and then for a shell that is further out, again, I'll try to draw it with some thickness. So on this shell that's further out, it's less, okay? Or sorry, it's more. So we have, if you plotted the rho versus r, it might grow in some way. It could grow, you know, linearly or not, but the point is that it is the same going out in any direction. It doesn't depend on which way you decide to set off. So what do you do about this? Well, when I originally talked about charge density, I mentioned that if charge density is a function, then you have to do something like this, okay? Only if it's constant can you pull it out. And then you get, of course, rho v, but we don't have that, so now it's a function that's got to stay in there. What do you do for dv? Well, these dv's are indeed still spherical shells, and so they have an area A and a small thickness dr. So that's what goes into dv is a dr. And what's a? Well, a, we're still in the spherical geometry, so that's going to be spherical shell. That's 4 pi r squared. And so that is exactly the same thing that you always put in Gauss's law on the left-hand side, and now it's here. So now Q is equal to rho, whatever function that is, and integrating with that function, you have a 4 pi r squared, and then dr. And this will get you your Q enclosed for Gauss's law. And then the only thing you have to decide when you're integrating here, so you have to make exactly the same decision you made before. If you're inside, then you only integrate out to the Gaussian surface. You might not get all of it. Whereas if you're on the outside, you have to be careful because the charge won't necessarily go all the way out to the edge of your Gaussian surface. You have to use big R. So a lot of it doesn't really change much, except for now you're doing some sort of integration, but that's pretty much it. So as a recap of the spherical geometry, here's what you do. Now this is the secret sauce. This is how you get these problems done super quick, okay? Here's what you do, okay? We're in the spherical geometry. This is 4 pi r squared. Little r is always the Gaussian testing surface. This is always little r, okay? That's it. Now Q enclosed over here, how much charge do you have enclosed? Well, if you're inside, that is to say R is less than big R, then you use rho times V enclosed. And remember, you used little r in there. Okay, so this you use little r. Okay, whereas if you're outside, then you're going to use big R instead. Okay, that's the only decision you really need to make. Okay, is on this right-hand side, do you use little r when you're inside or big R when you're outside? That's it. And again, if you have one of these cases, well, then you have to integrate rho times 4 pi r squared dr. This right here is your A, which is exactly the same as your A from this side. It's the your Gaussian surfaces. And then as far as what to integrate to, little r or big R, it's the same exact decision whether you're inside or outside. If you're inside, use little r. If you're outside, use big R, okay? So that right there will get you anything you need in the spherical geometry, and you're pretty much all set. Just remember again that the rho can at best be a function of r only, otherwise you cannot use this approach. So things that it's kind of problems that are like what I haven't already shown you, you could certainly have a hole, okay, but that hole had better be radially symmetric, otherwise you can't do it just like this. There are other tricks which I'll talk about shortly, where if the hole is off center, but the hole being radially, keeping the radial symmetry allows you to do that. What you just do is that in the V enclosed, you just subtract off the part of the volume that doesn't have any charge. So I think you have some homework problems like that. So that's pretty much it for the spherical geometry. And now that I've gone ahead and shown you that, the cylindrical geometry is going to be much, much quicker. So cylindrical geometry is going to be incredibly much easier. So for starters, I guess I will start with the line charge. So we have our infinite line charge, dot, 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 dot. And I mentioned that cylindrical coordinates would be the best for this, right? So you're talking about radial distance, r, angle, where are you around this, and z, which is going along with the axis of this. And if your charge density isn't affected by these, by the curtain test, your electric field can be expected to be radial as well. And so just by pure symmetry arguments, we can already sort of pretend, even if we had no idea, we hadn't already done this, which we have, we could easily reason that the electric field must be radial only. And so we have to think of what would be an appropriate Gaussian surface for this. For this, it's a cylinder. The cylinder goes around like this, like so. It has a radius r, so it's my testing surface. And then because it is a cylinder, it does have a length as well, so I'll call that L, okay? So a cylinder, so my Gaussian cylinder, it does have 3 sides, okay? So it has one curved side, and it has 2 end caps. Remember, this has to be a closed surface, so it has 2 end caps. Sorry, that says end caps, okay? So remember, this does have to be a closed surface, okay? So what does this look like? Well, the purpose of choosing, of course, the curved side is, of course, these normals on these curved side are going to point exactly in the same direction as the field. So for the curved side, this is going to just be EA cosine of 0. So that's +1. And then the end caps are actually kind of clever because the end caps, they stick out. The normals are going to be sticking out of the plane of the page, I guess. I mean, this is slightly 3D view, but essentially the normals to the end caps are sticking out of the page on the front side and into the page on the back side. And notice here that normal, no matter which of these field arrows we're on, those are going to be perpendicular to the field. And so for the two end caps, it'll be EA cosine of 90, and that's going to be 0. So in fact, all of our flux is going to come from the curved side. So let's go ahead and do this. Let's just start with the secret sauce here. Okay, I've already picked my Gaussian surface very appropriately so that this flux calculation is very easy. The area of this curved side, well, if you flatten it out into a sheet, if you take the curve out, of course, one dimension is the circumference of a circle, and the other dimension is just its length, so the appropriate A to use for cylindrical geometry is 2 pi RL. Now, what's my Q enclosed? Okay, so my Q enclosed, this is an infinitely long line charge, but I've only trapped some small part of it in my actual cylinder. And how much of the infinite line is trapped in here? Well, of course, L is the length that is actually contained in there. So Q enclosed would be lambda times L, right? My charge per unit length times the actual length that's inside, okay? So let's go ahead and see what I get. The L's cancel. That's really important. And the reason why is because L is a property of the Gaussian surface only. Okay, so it has no relevance to the charge distribution itself, right? This is just the testing surface we put here. We gave it an arbitrary length L, so we could just enclose some charge. But there's no, once you take away the Gaussian surface, L has no meaning in this system whatsoever. L is a property of the Gaussian surface only. It must cancel, okay? So when you are working in this geometry, if you have L left in your final field answer, you have done something wrong. Double check your work. Do not include L in your final answer. So luckily here we see that it does cancel. This is usually how it happens. There's an L on the always on the left-hand side from the area of the catcher, and there will also be an L somewhere here from the charge itself. So let's see what we get. The electric field is equal to lambda over 2 pi epsilon naught r, which, of course, should be well familiar from us already. We earned our stripes the hard way by getting this on homework number 2. Okay. So now you can again appreciate just how incredibly well Gauss's law performs in these certain symmetric situations. Okay. And in fact, same argument, the collapse idea. Okay. For anything that has a symmetry, once you go outside, the electric field will immediately go to this. Okay, I'm not talking about right away, or sorry, I'm not talking about far away. I'm talking about immediately, once you get outside, it will collapse onto this. I guess I should write immediately. These kind of collapse theorems, so to speak, are incredibly useful because they make getting the electric field, particularly outside, really super fast. Anything with that radial symmetry that's spherical, the moment you get outside, it just collapses onto the electric field of a point charge. And here, this actually, of course, is a infinite line charge, but anything that has this cylindrical symmetry, the moment you get outside, it will immediately collapse to that as well. Okay, that's the kind of curtain test. If you don't see that, you know, if this, for instance, was, say, a cylinder with uniform charge distribution, again, if you can't tell from rotating the cylinder like this that the charge looks any different, then the field shouldn't look any different. If you take this infinite cylinder and you shift it like this on the z-axis, well, of course, it's infinite, so how could you tell that there's any shift being made? And so you shouldn't see any shift to the field as well. So as long as there's no function, there's no dependence on these two in the charge distribution, you should not see any in the field either. Okay, so that's the outside, and then let's just do the, we'll there is no inside for an infinite line charge, but let's go ahead and look at a uniform row cylinder. Uniform row cylinder. So it looks like this. Let's work on this. Dot, 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 goes on forever. Let's start by working on the inside. So now I have to give my cylinder a radius, capital R, and I'm going to put my testing surface inside. So it's going to be something like this. I'm going to test what's going on. EA Q epsilon naught. This is always going to be 2 pi RL. And now, of course, I don't enclose all the charge. I'm only going to enclose some subset of it. So this will be rho times, and then the area volume of a cylinder is pi r squared L. And then here, remember, since I'm inside, I use little r. I haven't enclosed all the charge. I've only enclosed up to what can fit in the Gaussian surface. So let's see what we get. L cancels, pi cancels, and I get E equals rho r over 2 epsilon naught, okay? And by the way, comparing that to the sphere result when I was inside the uniform row sphere, for a sphere of uniform row, I got rho r over 3 epsilon naught. So aside from the fact that there's a 3 here and there's a 2 here, it's exactly the same result. Now, if you go all the way back to homework number 2, I think it was, I made myself a little catalog of all the functions. So let me see if I can find that here. And I did mention this briefly at the time, and I can come back to it now. So I made a catalog of every time that you extended your one dimension to infinity, what happened. So this was on homework 2. For a point charge in any finite charge distribution far away, it does go as 1 over r squared as you get far away. When we take one dimension to infinity for an infinite line charge, it goes as 1 over r. When we extend a second dimension to infinity, getting an infinite plane, it's constant. It's like every time I extend one dimension to infinity, I get an r, get to multiply by r. And that trend does tend to follow here. So every dimension that is extended to infinity, it's like multiplying by r on the electric field. So going from point charge to infinite line charge to infinite plane. And now it's not exactly that we have an infinite volume, but I do want to point out, and as I mentioned here, it was homework 4 that this is coming up. Welcome. So it is now proportional to r. So if we're inside a uniform row object, the electric field will go proportional to r. Now, this isn't quite the same thing, okay? This is just kind of a something, food for thought here. Now, if it was truly a volume that went to infinity, well, how could you be in the middle? What would be r equals 0? It doesn't really make sense anymore. But I do want to point out that as long as you are inside a cylinder or sphere of uniform row, even if it's a gigantic one, okay, even if you, for all intents and purposes for you, it's very, very, very large, as you go out from the center, the electric field will grow radially with distance, okay? The only difference is, of course, you could tell if you were inside a sphere or inside a cylinder because this one has a 3 and this one has a 2. You could also, of course, tell you were in a sphere versus cylinder because in a sphere, you can go out anywhere in 3D space, whereas in a cylinder, you better not mess up and start going along the axis of the cylinder because then the electric field won't grow at all. So here you have to go out, make sure you go out radially as far as the cylindrical geometry goes, whereas a sphere, you could go out in any direction in 3D space. But it's just some food for thought, going from just kind of remembering that every dimension that you add that goes that the charge exists in, you get to take an r out. So going from 1 over r squared to 1 over r to constant to r, okay? So from here, let me go ahead and examine the electric field on the outside. On the outside, you might say, doesn't it collapse to what I just said it does, the line charge? Yes, but let's go ahead and just do it for practice. And now my testing surface is on the outside. Doesn't hurt to redraw this again. So now there's the dimension of the cylinder, which is capital R, but I am testing what's going on at a little r, which is further out, to get what the field is going on out there. So E times 2 pi RL, that's always the case over here. And then the only difference, of course, is that now charge does not reside in the entire volume of the Gaussian surface. It only resides up to capital R. And so the only difference, again, let me do it in a different color. Instead of little r, it's going to be big R, okay? So rho pi big R squared L, okay? That's there. And that's epsilon naught. L's cancel, they better. Now we have some pi's cancel, but nothing else, because now this is always little r, this is now big R. So we go ahead and we get E equals rho big R squared over 2 epsilon naught, and let me go ahead and put in 1 over R. That's the electric field outside. Now, that's certainly proportional to 1 over R, but otherwise, it does not look anything like this. Let's rectify that. We will show that they are the same. Is that really lambda over 2 pi epsilon naught R? Yes, it is. Let me show you. Now, if I shoehorn in a pi here, a pi here, that's a pi. I can do that, right? I can add in a term in the numerator and denominator. They would just cancel. Then this 2 pi epsilon naught R is exactly identical over here. So it stands to reason then that this must be equal to this. So what exactly is going on here? So what does that mean? So let me show you why that makes perfect sense. If you have an infinite cylinder, you can slice it like a slice of bread here, like so. So each of these slices, it has a charge density of rho in this volume, and then of course the area of that slice is pi big R squared. So essentially what I'm doing here is that this is the charge per unit volume, and I'm multiplying it by the cross-sectional area, and that gives me the charge per unit length. So in fact, there are two ways to describe for an infinite cylinder what the charge density is. One is, of course, just good old charge per volume, but if you wanted to kind of segregate out that infinite length, right, you could do that. There's no problem with the cross-sectional area, that's finite, but if you wanted to sort of talk about the charge per unit length, you could, okay? So that right there is sort of like the effective, I could call it lambda sub f, EFF, the effective charge per unit length of this thing, because we're sort of reserving a special kind of idea for the one dimension of the cylinder that's infinite. So we want to kind of leave it as per length on that one, okay? So again, that's charge per unit volume, that's rho, times the cross-sectional area A, no problem, that's a finite cross-sectional area. That gives us the charge per unit length. Okay, so that's pretty much it for the electric field. And now, just to quickly address the voltage, well, there's going to be no huge surprises. Well, we already talked about, let's compare the electric field. So electric field looks like this. That's going to be the electric field grows radially and then goes off as like this. So this is proportional to r, this is proportional to 1 over r. You will actually find both of those functions agree on the surface. You can try it out, rho r over 2 epsilon naught. It's the same result in the from the sphere, except there's a 2 here instead of a 3. And now, as far as the electric field goes, or the voltage goes, well, we've already done all this work. We learned that outside, if the electric field goes as 1 over r, integrating that, we get, you can look back to when we did this the first time, you get this natural log function. And you get this natural log function where, again, the origin that you choose is going to be sort of arbitrary. So this is a negative natural log graph, proportional to negative, oh, there's a negative here, excuse me, negative ln r. Okay, and then inside, well, if this inside was identical, except for the factor of 2 versus 3, was identical to the electric field inside a sphere, well, the calculation is going to be pretty much identical here. It's going to look something like this. This is going to be proportional to negative r squared. Okay, same exact idea. When you're doing this, you're going to just integrate. It's going to be pretty much identical type integration, with the only difference that this voltage function on the surface is going to be given by this natural log function, so it's going to be ugly and not play nice when you go ahead and integrate. So you get blah 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 blah, and then some constant out here, and this constant cannot, like the sphere case, be folded in and simplified. It's just going to sit out here like this ugly natural log looking lump thing. So that's the voltage of this right here. This, of course, assumes that you want to set the voltage to 0 at some point outside the sphere. If you wanted to set it somewhere else, a good point might be exactly at the surface. That gives you something to tie to. Then the graph would look something like this. And again, that would have no functional difference whatsoever. You know, as you have some charges going along this, it's really the changes that matter, right? The voltage changes matter. So you can pick your origin freely however you want. So that's a little bit of the flavor of the cylindrical stuff. And then just to finish it off here, let me do again a recap of what you would do and talk about the non-uniform version. The non-uniform version, again, it can only be a function of r only. Then for Q enclosed, you'd have to do the integral form, and these volumes would be comprised of these sort of shells of area A and thickness dr. And the A that you use here, again, is just the A that is appropriate for this geometry. So in this case, 2 pi RL. And then again, your integration is going to go to little r or big R as needed, based on if you're inside or outside. So the recap for the cylindrical geometry, EA, Q enclosed over epsilon naught. A is 2 pi RL always. Don't have to worry about that. That's all always lowercase r. Over here, you could have rho times pi little r squared L. That would be if you're inside. You could have rho pi big R squared L if you're outside. That's the only decision you have to make. And then if you have a non-uniform charge distribution, this would be rho 2 pi RL dr. This is the same as this. You just throw it in there. And then the same decisions of inside or outside, you would make decision how you would put your integration bound. So the same decision here becomes a decision on the integration bound here. Okay, so I think that does it for this particular video. And I think you'll find that this video is largely the workhorse video for a lot of the Gauss's law problems in homework 4. And then there'll be a few kind of tips and tricks and other things that you need to consider in the next video to finish off this homework.